If you put 1 ampere of current through a copper wire with a cross-sectional area of 1 square millimeter, the electrons inside that wire move at approximately 7 times 10 to the minus 5 meters per second. That is 0.07 millimeters per second. A garden snail moves at roughly 1.3 millimeters per second, 18 times faster than the electron supposedly carrying your electricity, and yet you flip a switch and the light comes on. Not after several hours, almost immediately. For a circuit a meter long, the response can begin in only a few nanoseconds, far too fast to be explained by electron drift. The electrons that will eventually move through the bulb are nowhere near it yet. Something else is doing the work. The wrong picture is this. Electrons leave the battery, travel down the wire like water through a pipe, arrive at the resistor, dump their energy, and return. It is the picture almost everyone learns first. It gets the current right, the voltage right, and the power calculation right. But it gives the wrong answer to the deeper question. Where is the energy while it is moving? The answer is not inside the wire. Not in the way the ordinary picture suggests. The energy is carried by the electromagnetic field around the wire, guided by the conductor, shaped by the geometry of the circuit, and delivered into the load through space. The wire matters. The electrons matter, the current is real, but the energy flow is not a stream of tiny particles racing through copper. That is not a poetic interpretation. It is Maxwell's equations applied to an ordinary circuit. Start with the surface explanation, because it is not false. A battery maintains a potential difference between its terminals. Connect a circuit, and an electric field is established along the conductor. That field pushes the mobile conduction electrons. They drift slowly through the metal, colliding with the vibrating lattice of copper atoms. In a resistor or filament, those collisions convert electrical energy into heat and light. This is Joule heating. The power dissipated is P equals I times V. 1 ampere through a 1 ohm resistor with 1 volt across it gives 1 watt, 1 joule per second. Everything in that paragraph is correct. The drift is real. The collisions are real. The heating is real. Engineers use these equations every day because they work. But they work as a compressed description. They do not show the mechanism underneath. Copper has roughly 8.5 times 10 to the 28th conduction electrons per cubic meter. 1 electron carries a charge of 1.602176634 times 10 to the minus 19 coulomb. 1 ampere is 1 coulomb per second. If you use the drift velocity formula, velocity equals current divided by number density times charge times cross-sectional area, the result for a 1 square millimeter copper wire is about 7.4 times 10 to the minus 5 meters per second. The number refuses to explain the lamp. So the electrons shuffle, the field delivers. This is where the physics stops being intuitive and becomes exact. In the 19th century, Maxwell unified electricity, magnetism, and light into one mathematical structure. Faraday had already shown that changing magnetic fields could produce electric currents. Ørsted had shown that electric current could deflect a compass needle. Ampere had measured the magnetic effects of currents. Maxwell's crucial addition was the displacement current, the idea that a changing electric field can produce a magnetic field, even where no charges are crossing the space. The capacitor made this unavoidable. Current flows into one plate of a charging capacitor and out of the other, but no conduction current crosses the empty gap between the plates. Ampere's original law gave different answers depending on how you drew the mathematical surface. Cut through the wire, and current passes through. Bulge the surface through the capacitor gap, and no charge crosses. The same physical situation seemed to produce two different magnetic fields. That cannot be right. Maxwell fixed it. Between the capacitor plates, the electric field is changing. That changing electric field acts like a current for the purpose of producing a magnetic field. With that term added, the equations became consistent. They also predicted electromagnetic waves moving at a speed determined by epsilon naught and mu naught. That speed was the speed of light. In vacuum, light travels at exactly 299,792,458 meters per second. Electricity, magnetism, and light were not separate subjects anymore. They were one field theory. Now take that same field theory and apply it to a resistor. A steady current through a resistor requires an electric field along the resistor. Without that electric field, charges would not drift through a resistive material. At the same time, the current produces a magnetic field circling around the resistor. For a long straight conductor, the magnetic field wraps around the wire in closed loops, so there are two fields at once, an electric field along the wire and a magnetic field around the wire. They are perpendicular. And the flow of electromagnetic energy is given by the Poynting vector. In spoken form, the Poynting vector is S equals 1 over mu naught times E cross B. E is the electric field, B is the magnetic field. Mu naught is the magnetic permeability of free space, about 1.256637 times 10 to the minus 6 newtons per ampere squared. The cross product tells you the direction in which electromagnetic energy flows. Its units are watts per square meter. Apply that to the resistor. E points along the wire. B circles around the wire. E cross B points radially inward through the surface of the resistor, from the surrounding space into the material, not along the wire into it. If you integrate the pointing flux over the surface of the resistor, the total energy per second entering the resistor equals I squared times R, exactly the joule heating. The power that appears as heat in the resistor is matched by electromagnetic energy flowing inward from the field around it. The numbers close. The conservation law is exact. This is the result Feynman emphasized in the Feynman Lectures on Physics, Volume 2, in the chapter on field energy and field momentum. He takes a resistance wire carrying steady current and follows the calculation. Because the wire has resistance, there is an electric field along it. Because there is current, there is a magnetic field around it. Their cross product points inward. The energy flows into the wire from the surrounding field, not down the inside of the copper. It appears crazy only because the usual picture is too simple. The same mechanism becomes even clearer in a capacitor. A parallel plate capacitor stores energy in the electric field between its plates. The field energy density is 1/2 epsilon naught times E squared. Epsilon naught is about 8.854 times 10 to the minus 12 farads per meter. As the capacitor charges, the electric field between the plates grows, and the stored energy increases. Where does that energy enter the gap? The naive picture says it comes down the wires into the metal plates and somehow appears between them. Maxwell's equations say something different. As the capacitor charges, the changing electric field between the plates produces a magnetic field circling around the gap. The electric field points from one plate to the other. The magnetic field circles around the axis. Their cross product points sideways into the gap, through the cylindrical surface around the capacitor. The energy enters from the sides. Again, if you calculate the pointing flux through that side surface, you get the rate at which field energy inside the capacitor increases. Not roughly, exactly. The wire brings charges to the plates. But the energy stored between the plates arrives through the surrounding electromagnetic field. This is the part ordinary circuit diagrams erase. A circuit diagram is not a map of physical space. It shows connection, not geometry. It tells you what is connected to what, not where the fields are, where the surface charges sit, or how energy flows through the space around the conductors. In a real circuit, surface charges distribute themselves along the outside of the wires. They are not uniform. Their pattern depends on the battery, the load, the bends in the wire, nearby conductors, insulation, and the full geometry of the circuit. These surface charges create the electric field that drives current inside the wire and shapes the field outside it. The current creates the magnetic field. Together, those fields form the energy flow pattern. The circuit is not just the copper. The circuit is the copper plus the space around it. Transmission lines make this impossible to ignore. In a coaxial cable, there is an inner conductor and an outer conductor. The electric field points through the insulating material between them. The magnetic field circles the inner conductor. The pointing vector points down the cable through the dielectric space, not through the metal. The conductors guide the fields. The energy travels in the field between them. This is why geometry matters. This is why impedance depends on conductor spacing and dielectric material. This is why damaged insulation can ruin a signal. The signal is not merely in the metal. The electromagnetic field in the space around the conductors is carrying the power. At low frequencies and short distances, we can ignore most of this and use Ohm's law and Kirchhoff's rules. That is not a mistake. It is a powerful approximation. But it is an approximation. When circuits become large, fast, or high frequency, the field picture stops being optional. Signals reflect, cables radiate, energy leaks, timing matters. The space around the conductors becomes the engineering problem. The simplified model works until the thing it ignores becomes important. Feynman's point was not that beginner circuit theory is useless. It is that beginner circuit theory is not the bottom layer. Voltage and current are compressed field quantities. Voltage is related to the electric field integrated along a path. Current is related to magnetic fields circling conductors. When you write P equals V times I, hidden inside that compact formula is the same energy flow described by E cross B. Circuit theory is Maxwell's field theory folded into a simpler language. That is why both pictures can give correct numerical answers while only one gives the correct physical mechanism. The electron drift picture tells you what charges do inside matter. The field picture tells you how energy moves through space. They are not enemies, they are different resolutions of the same event. Now look again at the battery. A battery does not fire energetic electrons through a copper tunnel. It uses chemical reactions to maintain a separation of charge between its terminals. That charge separation establishes an electric field in the space around the circuit. When the switch closes, the field configuration changes. Current begins. A magnetic field appears. The pointing vector describes energy flowing from the source region toward the load through the electromagnetic field. The battery sets boundary conditions. The wire guides the field. The load receives energy from the field. This is a very different image from the one most people carry. It means the apparently empty space around a wire is not empty in the electrical sense. It contains electric field, magnetic field, energy density, momentum, and stress. The power delivered to a lamp is not a substance hidden inside copper. It is an electromagnetic flow shaped by copper. This is why the phrase "electricity does not flow through wires" has to be handled carefully. If by electricity you mean charge, then charge does move in wires. If by electricity you mean electrical energy, then the ordinary picture is wrong. The energy is in the field. The wire is the guide. Feynman's way of handling this was simple. Do not ask what feels right. Compute E, compute B. Take E cross B and divide by mu naught. The result gives the energy flow. In a resistor, it points inward from the surrounding space. In a capacitor, it enters through the sides. In a coaxial cable, it travels through the dielectric between conductors. The same rule keeps appearing because the same physics is underneath. The strange result is not an exception, it is the rule. So when you flip a switch, the electrons in the copper do not race from the wall to the bulb. They begin to drift slowly under the influence of the electric field. But the electromagnetic disturbance travels through the circuit environment at a large fraction of the speed of light. The field reorganizes, energy flows through space, the load absorbs it. Then matter turns it into heat, light, motion, or sound. The lamp does not wait for an electron to make the journey. It responds to the field. This is the physical picture that survives the calculation. The wire is visible, so we mistake it for the path. The field is invisible, so we treat it as secondary. Maxwell reversed that. Pointing measured the flow mathematically. Feynman forced the beginner's circuit to confess what it had been hiding. The conductor is not the highway for energy. The space around it is. The electrons drift slowly. The field races. The wire only shows the field where to go.